Hey, how you doing? Welcome to today's lesson. What we're going to be looking at today is applying integration. Okay, so working out, well, not really applying integration, because I would be using applying integration to work out other things like areas and differences between two curves, for example. But what we're going to be looking at here is more specifically particular solutions. Okay, so this is when we have an integration through a point that will allow us to find a particular constant of integration. So you need to know how to integrate normal polynomials just straight up. Okay, so let's see. The example that I work through in this one is I'm going to say if I've got dy by dx, a differential equation equal to x cubed plus 3 over x cubed. Okay, and they say find the function of this gradient, right, that passing through, what have I got there? 1, negative 1, 1, negative 1, right? Okay, so very straightforward. The first thing, this is our derivative. We need to find the actual function. So the first thing we're going to do is we're going to integrate this. Number one, we're going to integrate x cubed plus, I'm going to tidy this up into the way that I like it. So I'm going to write 3x to the negative 3 with respect to x. Okay, all I've done is brought that negative, the power to the top of the line, change the sign from positive to negative. Okay, now integrate each one of these, and I've got the integral of this is x to the add 1 to there, 4 divided by that. Alright, x to the 4 divided by that. And then the integral of this is leave that 3 there, x to the add 1 to there, negative 2, divide by negative 2, plus some constant of integration. Let's just tidy this guy up. X to the 4 divided by 4, 3 times negative, the negative 3 over 2, x squared plus some c. Everyone with me? Awesome. Okay. In the notes, I've actually done it slightly differently. I've left that negative at the top there, but bring it down to the bottom. It doesn't really make a difference. Okay. Right. So now that's the first step. Integrate the whole thing. Step 2. I'm going to sub in that point 1, negative 1. Right. So I've got y equals this. This is my actual function. Okay, because I've integrated. This is the general function, right? Now I've got y equals negative 1, so I'm just going to put negative 1 in for y equals, well, whenever x is 1. 1 to the power of 4 over 4 minus 3 over 2 times 1 to the power of 2 plus the sum c, and I'm going to solve for c. Okay, tidy this whole thing up. This is a linear y, highest power is 1 of the variable that I'm using. A linear equation. Really, you should be able to solve this straightforward in your sleep, right? So I get here c is a quarter, right? Okay, so if you solve that linear equation, you get c equals 1/4, and then you're done, right? You're basically finished, because all you have to do is rewrite the equation. So the equation that would give me this derivative is y equals, what's it? X to the 4 over 4 minus 3 over 2x squared plus 1/4, plus 1/4. Done. Okay. Now, very briefly, okay, if the reason why you have to find that exact number is because when you differentiate, all of those c's also disappear. Now that's a very good thing to quickly look at, okay, look at with a quadratic. If I had a quadratic, let's say x squared, right, there's x squared, okay, derivative of this is 2x, right, derivative of this is 2x, y dash, let's just do y dash, it's 2x. If I had x squared plus 2, x squared plus 2, the derivative of this, y dash, is still 2x, right? If I had x squared minus 1, x squared minus 1, right? Okay, it's not a proportion. The derivative of this, y dash, is still 2x. So basically, what we're saying is with all of these, the gradient is still the same. Okay? It's just that the shift is slightly different. This is why whenever you integrate, you'll get the general solution. You'll get a general gradient that's going to give you this, alright, gradient, but it's exactly the same as this gradient. Okay? And it's exactly the same as this gradient. Are you with me? Okay? And what you need to do is find a specific solution by taking one of the points in reality and plugging them into No, that's wrong. We have to plug them into that to find out the C value. Does that make sense? Okay, awesome. Pretty straightforward. This happens for almost all of integration, okay? Don't forget your constant integration and just plug the coordinate of the original to find out the constant. It'll always end up being some kind of linear equation that you have to solve after you've got all of them out. Okay, hope this helps. Remember, there's more now.